Perfect. Yeah, so good afternoon, everyone. In this talk, so I will be trying to give some insight and some information about transformer models, especially those ones here are trained for Arabic. And yes, okay. Yeah, so just before starting, I will just give some motivation about why we are doing this this task, basically, where we want to understand what's going on with Arabic transformer models. So there is one thing that we have seen that the last year and a half, almost less than 2 years, we have seen like a big number of transformer models that become viable within this frame of time. And these models, luckily, so they have achieved like a really state-of-the-art performance in number of downstream tasks. And the issue is, so yes, they did well. The architecture is novel. They did good performance, but so what are the limitations? Why they have achieved this high performance, and what is the information that is being captured in these models that give them this edge? So before diving further into the transformer models and then specifically the BERT models, so I will give some background about the word embedding and numerical representation for the words. So this idea of representing words as numerical vector, so basically it was a major breakthrough in NLP domain. And so this kind of modeling allowed to do a lot of tasks that they were not available before, like in statistical models or maybe rule-based, whatever. So we cannot, it's hard to do do a lot of measurements. And so using this representation, so we are able to do word similarity, word dissimilarity, looking at the semantic relationship of the words. So define word within context and do also, I mean, because now it's everything representing in a numerical form, so we can do visualization. So if we take this representation, which is in n dimension, and then we do some reduction, some dimensionality reduction, we can be able to visualize them using some method like PCA or UMAP or Tisney and so forth. So here, just I'm giving you an example. This is just a projection for a list of word vectors using Tisney. So as you can see, so this map here is not completely random. So there are a lot of information being coded here, and the neighboring, or for example, distance between words are not completely random. It's not by hazard. So as you can see, for example, here in the top left, you can see the words that are all start with ta, as it was in Arabic. So this is an indication. Maybe these verbs here, most of them are like in present tense. And for example, there is another cluster here to the left, with qama, yaqumu, qumtu, aqumu, and so forth. So this is also same verb, but within different tenses. Maybe if we can look further here in the bottom here, so there is mada, limada, mal, hal. So this kind of preposition and so forth. So basically, so there is some information that's being captured by this word vector, and you can visualize it and we can see it. And maybe further here to the numbers, so there is idda, thalatha, arba'a, ashara. So this is all numbers. So you can see there are a lot of information being coded here, and it helps to do a lot of analysis. It facilitates to do a lot of analysis using these methods. So this is for the word vector, the word2vec, for example, as a presentation for the word embedding models, the first generation. So, but this type of modeling has some limitations, as we can see in this example here. For example, I was late to school after stopping by the pond, or I was watching a school of fish. So the problem with word2vec doesn't differentiate between these two senses. So it takes one word, one form of the word, and it presents it as vector. So it doesn't represent the meaning, but rather it presents the word form. And so this is the case also for glove also. For the and so later on, maybe after a few years later, so there is new representation. I mean, starting with the ELMO, the embedding from language model, and also BERT, bidirectional representation from transformers, and generative pre-training, GPT. So these new generations, they do try to attempt to fix the problems that they have there was before in ELMO and BERT, in word2vec and glove. So the advantage of, like, for example, for one of these transform models or BERT, as an example, so it does use encoders rather than, for example, looking at just a language model by itself. And also, the advantage also, it incorporates context, which is not captured much in the former models. So it captured model from both direction, left and right, and so forth. So the architecture of this, specifically for the BERT models, so they are just a stack of transformers. You have like a 12-layer block of transformer blocks with an attention, and also there's hidden neurons in every layer. For the BERT base is 768 neurons, and for the large is like 1024. So this is just some information. We will look at it later on. Okay, so starting from when the BERT models became popular, so a lot of people have attempted to understand exactly the new representation, or what this representation means. And by looking at different components of the BERT transformers, so for example, looking at the embedding layers, looking at the layers themselves, the middle ones, or looking, for example, at the attention, or looking at the neurons themselves. So there are a wealth of literature that have been published about looking at different BERT models, especially for the English model. And so going back to the Arabic models, so in the last, as I said, in the last maybe year and a half or 2 years, I have been able to enumerate like around about 40 models that are available now in Hugging Face, and from various places in the world. And also these models, they are not all the same. So they have some differences either in the training data, the way they were trained, or the vocabulary size, or the data type itself, not just the size, but also do they include like MSA, do they include like a classical Arabic, dialectal Arabic, and so forth. So in this study here, basically, I will focus on 9 models to compare them together. And basically, so I'm going to use some of them which included like basically Arabic, but some of them also includes like classical Arabic and dialectal Arabic, same like the case for Arabic BERT, for Kabul BERT, Mar BERT, Karib, they do contain, in addition to MSA, they do contain dialectal Arabic. And as you can see, so basically the size of the data that has been used for training varies widely from from a couple of billion tokens to trillions for the case of XLM. And also same thing for the vocabularies. So they do vary the vocabulary from from 32K or 30K for the camel bird to almost like 250K vocabulary size. Although vocabulary size probably is a little bit not representative, as you know, because most of the Arabic models, BERT models, sorry, they use word piece. So basically, even the word, if it's not in the directly modeled in the vocabulary, and the original still can be able to capture its sense using its component, or when we split into BP. Okay, so for this task here, we are looking at to be able to understand these models. I'm using like 3 tasks. 2 of them are about part of speech tagging, which is the ATB, the Arabic Tree Bank, which contains around 20,000 sentences that been tagged at the segment level with, I think it's about 40 tags that has been used for tagging. And when you combine them, basically for every word, you will find sometimes like, for example, determiner plus noun plus maybe noun suffix. So this combination will end up about 220 or 200 different tags. For the dialectal Arabic, so it's similar thing, although the data is way small, so it's only 1,400 tweets that has been collected from to represent 4 Arabic dialects: Egyptian, Levantine, Gulf, and Maghrebi dialect. And so also they are tagged at the segment level, at what level? Segment level. And the last task is dialect identification, which is basically just code switching data that is labeled with 8 labels, like for example, say language 1, language 2, or mixed and noun, named entity, and other and so forth. And so this is the task that we will be looking at when we explore these models. So for the methodology, how we are going to do it. So this is just kind of an outline for the process that we use. So basically, we just take the representation of BERT, take an X model, one of the models I've seen from mine. So for each word, we dump the representation using the Neuro-X toolkit. So we basically, we're on the top of these representations with the tags that are expected to have. So we use a linear classifier with the elastic net regularization. And so we use categorical cross entropy for optimization. And then we train every classifier for 10 epochs, and then we compute the accuracy. So here, just small notes here for the representation for the individual layers, because we'll be looking at the individual layers, and also we'll be looking at the neurons. So for the layers, so we dump every layer by itself. And for the neurons, we take the whole thing and then we sort the neurons. So basically, the formula, this is the formulation. So as I said, so let's consider a model M. We'd have, for our case here, we have 12 layers from 1 to L. And then we have a data set contains words. And every word basically have its corresponding linguistic annotation, like for example, for our case here, either part of speech or dialect identification. So for every word, it has a corresponding tag. And then, so we do this map. So we will be looking for probability of for Z that assigns a specific tag. So the objective function we have is to minimize this loss function, which is the log probability of for word I to be assigned property, TWA. So doing the first analysis, so this is like an overall performance for all these models. So we can see that the numbers are not completely bad. I mean, most of them, like for example, for the ATB, we are in the 90s, 95, 96, 94. For the dialect identification, we are in the high 80s. Same thing with the dialect identification or the code switching, we are in the high 90s. So the numbers, they are looks very promising. And even some of the models here, they do perform not as good, but this is probably will be an indicative of the data set. So let's look here for a better representation for these numbers here. So as we can see, like for example, say this group here, which is like a Qarib, this is Marbird, this is Camel bird, and this is Arabic bird. So this group here, they are all trained using MSA plus dialectal Arabic, and this, you can see that they are performing well in both like the tasks that are related to dialectal Arabic, and here for code switching, so they do dialectal MSA, and even here for MSA, yes, we can see that Electra is different, is performing as well as very competitively than the other one, but as you can see, the models that they contain Arabic and dialectal Arabic, they do perform significantly good. So like, for example, for this case here, for dialectal Arabic for part of speech, like this one here, MBERT, multilingual BERT, because it contains only Wikipedia, which is like not that much diverse, so it performs the worst. And so let's dig further. So this is just a recapitulative slide about what we have seen in the graph. Basically, as I said, so we have Qarib, Marbird, and Kabbird perform better. Dialectal models perform better than the other ones, and MBERT performed basically the worst. Now let's look at the overall performance, but per layer for every of these tasks here. So just for convention here, so basically because we have like 3 or 4 models, they are trained on almost same data. So basically we are going to replace this 4 here, the 4 here with only one model, one of them, which is Camelbird, because they do behave the same all time. So as we can see here, the performance, so what happens now, for example, so this is basically the performance of every layer the first layer, which is like the embedding layer 0. So most of them, they perform less, but the more we go deeper inside, the performance gets better. So means like that the layer inside, like for example, from between layer 5 and 6 till 8, there is kind of a top where this is where the best performance we are achieving it. So this is for ATB. So let's look for something for Camelbird, for the dialectal Arabic. So we can see here that for this case here, Camelbird, or the model that are trained on dialectal, so they do achieve significantly higher than the other group. And the one trained on only MSA, which is like a multilingual BERT and BERT, so performed the worst. And there is some slight drop at the end. So the more you go to the top layer, there is a drop in the performance. So same thing for direct identification, which is code switching. Here we don't see that dip, where at the end of the last layers, so here all the layers they do keep the same performance until the end. So this is something different than what we have seen for the previous models, which they tend to go down on the higher layers. So here is also a kind of summary. So we can see that the accuracy of MBERT and ARABERT, because they are trained only on MSA and not any dialectal Arabic, they perform low. There is improvement in from the embedding layer to so the more you go deeper inside the model, the better or the more performance you see. And also, there is marginal change in performance at the higher layer after the first few layers, as we have seen in the direct identification and also in the ITB. Okay, so we looked at the layer. Now let's look at the neurons, how they are distributed. So we know that like for every level, every layer, so there is about 700 neuron that is being captured for that's been used in every task. But we can see here that some of so not all the 700 neurons are being used for these tasks here. Like for example, I say, yes, Albert has different architecture and it does have some, they do replicate layers as they are, so that's why it behaves differently. But for the other ones, we can see more or less kind of the same trend, that like, okay, there is like the embedding layer is largest, and then the more you go inside, there is less neurons involved in the task. And maybe at the end, there is also the top layer that has like, it fans out, it has more neurons in the top layer. It's a little bit different for the direct identification, direct part of speech tagging. So here we have it's kind of going, the deeper you go in the model, the more neurons are being involved in the tasks. And the same thing, we can see it here in the direct identification. So we can see back the same issue where the embedding layer and the last layer are use the most neurons. And the same thing. So we have Albert basically has this kind of the hump here. It has like in the second layer, which is kind of indicate like it's different architecture than the BERT models we looked at. So back again, this is some summary for what we have seen. So we have seen like a large number of the top neurons are from initial layers, and also for the last layers. And for the last layers, our intuition indicate that like probably the last layer, the last numbers, because due to the objective function that you use, so try to optimize the representation of the last layer specifically. This is why it has its direct reach. So that's why probably it involves more. It tries to maximize the number of neurons that are being used at that level. And also for Albert, so we said that behave differently due of its own architecture, using the loss and also using the repeating layer. And okay, so we have seen basically layer an overall performance, and we have seen the layer-wise performance, and we have seen neuron-wise performance. So next one, we'll dive further and we look at property-wise performance. And so basically we do the same thing, and we try to see how many, first of all, what's the performance of the neurons, the performance of each model for each property, and further we are going to look at the neurons per property as well. So this is like a summary. This is just some selected tags from ATB, and this is their performance. And as we can see that, I mean, most of the tags, they do have like high performance, except some of them here. I mean, like for example, say the verb. Some forms of the verbs, they do have even some of them, like because they have a very low performance. And also those ones here, like for example, this one here is because it's kind of a closed class, like for example, say the preposition or pronoun and so forth. So those ones here are limited class, and that's why probably they perform low. And also same thing when we looked at this form of verb, I think they performed very low because their representation, they do have enough representation inside the corpus. Their frequency is very low. So this is the same thing, the performance for the dialectal Arabic. As I mentioned before, the dialectal Arabic has less granular part-of-speech tagging, so it's not like the ATB, which is like about 42 tag. So the dialectal Arabic, I think, has less than 20 tag and also because it's tweet, so we do have different additional tags like emotion and hash, and I think URL as well. So probably is not here, but in overall here, most of them have achieved like higher accuracy above 80%. So here the adverb, I don't know, their performance here is moderately low comparing the other tags. And most probably because it's due to the frequency of the adverbs when it compares to the other tags. So this is for the direct identification. So as you can see here, so there is a good performance for low for the overall for the language one, language two, so it's be able to distinguish. But you can see when it's ambiguous or it's mixed. So there is this is where the majority of error coming from the word that are ambiguous, because they are ambiguous and so forth. So the system, maybe it's hard to determine them as accurately as possible. So this is in sum for the property-wise. So we can see that frequency of property impacts surely impact the performance, and also some tags are very complex. Like for example, say the closed class, because they are limited, and also their usage sometimes is very polysemous. And it's not like, for example, say noun. Noun are well defined, and they do have their own users. Okay, and then okay. So next, so as I mentioned, so we looked at the overall performance of tags. Now let's see how many neurons every tag it uses inside the models. So for this, I will be using like try to use one or two models, and then you'll see the distribution of the tags inside the every model. So here we know that, like for example, for Arabert, so it's only trained on MSA, and we can see, so although there is the same behavior that it's from the beginning, they do have many neurons in the embeddings that contribute for embeddings, but also the last layer has been neurons involved. But in the middle here, there is like a very limited number that involves any of this. Like for example, say this is like this three here, which is adjective, noun, and verb. This is like open class, and CC, the determiner, and ejection. So this is like closed class. So you can see, I think this is almost kind of intuitive here from this graph here, that some of this closed class, although here is not well pronounced, that they do use less than the open class. So let's see, maybe for here it's much more clearer for Camembert, because Camembert uses like large, it was trained on larger corpus, and also it does include dialectal Arabic, which means like the representation is much more rich. So you can see here this first three here, which is the open class, they do use more neurons in almost like every layer, versus the closed class, which is like, for example, say here, the green and orange and the blue here. So although it's different, but some cases it uses same as open class, but overall the closed class use less neuron than the open class. This is the same behavior using the Ambert. So we knew that the issue with Ambert that doesn't have, it's not rich presentation, but still you can see some of the still same behavior that we have seen in the other models where the closed class, where the open closed class use less neuron. Okay, so after when we looked at the neuron here, we would like to ask another question, which is like, okay, how much of these neurons are common between these properties? So when we look at the neuron, we call it neuron overlap. So this, we can see here this is for the overall neuron, and we can see there are some clusters basically. So this cluster here is determinant and adjective and noun, and we know that in Arabic that both determinant, noun and adjective, they use determiner, because they do have, like, for example, say al-bayt, al-ahmar, al-akhdar, so forth. So there is this is good usage, or it does indicate some kind of co-location or coexistence of these two these properties together. And same things, like, for example, say we can see another group here on the top, which is related to the adjectives, like adjectives and conjunctions and what else? CD. So CC is conjunction. So for example, say wal akhdar wa something. So there is always like the word, the conjunction is attached to the nouns, is attached to the adjective, and so forth. And also there's a lot of cases where determiner is attached to co-located or coexist with the conjunctions. There is another group here which is like very unique. Probably we'll discuss it later on, which is like the relation between determiner and verbs. Although most of the time, for example, there is no direct relation, but we will see why we have this kind of dark blue, which means like there are some significant number of neurons that are common, or they are shared between these properties, which is like the verb and like the determiner, adjective, and nouns. So basically, normally in the normal world or normal case, you think that you're supposed to see only like the column here, the diagonal in the black, and the rest they should be white. But this is not the case for Arabic, so it looks like there is a lot of commonalities between the neurons at different levels. Okay, so we are looking now at the neurons at all the layers together. So now let's look at layer per layer and see if we can find something, anything interesting in this. So when we look at the layer per layer, so we can see that okay, so this is layer 0. So layer 0, this is embedded layer. So as we see, so maybe there is less common neurons in the here outside the diagonal, and we can see the contribution of this embedded layer almost like it's very small comparing to the other. So there is this still the same cluster of the noun and determinant and the adjective, because they do share most of the time the nouns and the adjective that are together, and also with the determinant they do collocate together. And same thing for the verb. It seems like there is a relation between verb and the noun, because like for example, say you have verb and subject, or verb subject and some adjective and so forth. So this is for layer 0. Layer 1, we can see still the same behavior, although maybe this group we have seen with the adjective and the verbs is no longer here at the layer 1. And the layer, when we go to the middle, basically the neurons became what we call them much more specialized, because there is no overlap anymore between the neurons. So the neurons, they are very specialized. So there is a neuron for adjective, or for conjunction, or for noun, and they are only handling that specific tag. So same thing here, still in the middle layer. But when we go to the higher layer, so we can see different feature. So there is this overlap. It comes back again, and there are some small clusters that they are showing here one more time at the higher level, which is the top level, like for example level 12. So we have back the same issue with group with the verbs and determinant and noun, and we have that group also for the adjectives, noun, and determiner all together. So I think I have basically represented, so this is just a kind of a summary. So we have seen that properties they do share neuron cross layers. So the ratio of this intersection sometimes reach very high, as we have seen, like for example, say the layers we have seen in the beginning. So some of these neurons here are significantly, this is almost like 50% of neurons that are overlap between the noun and the determiner. Sorry. And also, so as I mentioned, because the word in Arabic, so there's a C missing here, cause the collocation cause in this overlap. And also the middle layers, mostly we don't see that much overlap, because the middle layer are much more specialized. And also the higher layer capture long dependencies. This is what we have seen, like again, that appeared again for the relation between determinant verbs, because there is long dependencies and these long relations that's being captured at the higher layer, same as like for example for the verb and determinant, that they do share neurons at the higher layer. So in summary, for this work and what's coming hopefully in the near future, so we have training data matters, that's kind of take home message, but also the architecture and vocabulary size, maybe they do matter less. So the dialectal models are more generic and are more rich. So the linguistic knowledge is spread across neuron and cross layer. And also the middle layers, even for the case of our models here, they do have specialized neurons versus like the higher neurons, which are more polysemous. And so for the future work, so we are looking at the way to analyze, make more tasks, and also try to compare such distribution or such properties, if they do hold for different languages. And also, as I mentioned, so we need to analyze properties deeper for maybe for specific tasks. If we can see, for example, say for the verbs, if we can eliminate some of them or maybe put them to zero, what's going to happen to the outcome. So I hope I have shed a light on these models, and it was very informative. Please, if you have any question, please don't hesitate. Thank you very much.